Hello and welcome back to this series on CNNs. Previously, we had discussed the convolutional layers in a CNN and what operation the convolutional layers perform. And in particular, we had seen how the convolutional operation, which is performed in the convolution layers, affects or alters the dimensions of the data to which the convolution is applied. Specifically, we had seen how the width and height of the data as well as the depth of the data gets altered as a result of the convolution operation, and we also got the relationships between the dimensions of the input data, the filter size as well as the output data. So we have seen what are those relationships between the dimensions of the data, and we have also seen how we can control those dimensions by using specific techniques during the convolution process. In this video, however, we are going to explore a few demonstrations of the convolution operation using specific filters, and we will demonstrate how by using specific filters and performing convolution with those filters, we can extract certain specific features from the input image. For example, if we had to detect the edges in the image or the edges within the objects of the image and so on, we can use specific filters to extract those features. So we will be seeing a demonstration of the convolution operation using specific features in this particular video. But before we actually go into the demonstration of the convolution operation, let us quickly recap what we had seen previously regarding the convolution operation. In particular, we had discussed earlier that the convolution operation affects the dimensions of the data in terms of its width, its height, and also its depth. And these dimensions can be controlled. That means the dimensions that we get at the output can be controlled by controlling the size of the stride, which is the number of pixels by which the window jumps across as it moves along the image. And we also saw how we can use padding to control the dimensions of the output image. And we also saw that we can control the number of channels, which is which in other words called the depth of the output image. How we can control the depth by adjusting the number of filters. So let's quickly see how we did those things and then move on to the demonstration of the convolution operation. So to begin with, we have seen how performing a convolution operation reduces the dimensions of the data. So a 6x6 input image after convolution has become a 4x4 output image as a result of the convolution operation. And in this case, we had used a stride value of 1. Similarly, if we increase the size of the stride, then we get a much smaller dimension for the outputs. For the same input dimensions of 6x6 and the same filter size of 3x3, when we increase the stride value for the window from 1 to 3, the dimension of the output is now 2x2 instead of 4x4. So we see that increasing the stride value helps in reducing the size of the image. And then we also saw how we can control the width and height of the output image by performing padding on the input image. So there might be situations where we want the output size to be the same as the input size, in which case we can use some padding of pixels around the actual input image, and that way we can get an output image which has the same dimension as the input image. In this case, the input image is 6x6. We use a padding layer of 1 pixel all around the input image, and performing the convolution with the same 3x3 filter results in an output image which is also 6x6, which is the same dimension as the original input image before padding. So there can be situations where we want the output dimension to be the same as the input dimension, in which case padding is quite useful. The other advantage of using padding is that the pixel values which are at the corners of the input image, they are used more often in the computation, and that way it gives us more information about the pixels at the corner of the input image. So padding has that added advantage as well. But for the purpose of this discussion, we will restrict our attention to just saying that padding helps in controlling the dimensions of the output image with respect to the input image. So we can choose the amount of padding that is required in order to obtain a specific dimension for the output image value. The other aspect in terms of dimensions as a result of convolution was regarding the depth of the output. So irrespective of the number of channels we have in the input, in this case we have 3 channels in the input, the red channel, the green channel, and the blue channel. And if we perform a convolution of this input data or this input image with a single input filter, the output will have only a single channel. However, by using multiple filters, we can have multiple channels in the output. So if we use 2 filters, the output will have 2 channels. If we use 10 filters, the output will have 10 channels. Or in other words, we say that we can control the depth of the output by selecting appropriate number of filters for the convolution operation. So if we want a depth of 6, then we will have to use, say, 6 filters in the convolution operation, and so on and so forth. So the depth of the output is controlled by the number of filters that are used in the convolution operation. So what is the objective of today's lecture? We want to understand the convolution operation using some demonstrations of the convolution using some real-world images. And we are going to use particularly some images of handwritten text characters and perform convolution with certain specific filters to extract specific features from the input image. In particular, we would be interested in extracting the edges of this handwritten character. So we want to determine where is the left vertical edge or the right vertical edge, or where is the top horizontal edge or the bottom horizontal edge. So we want to locate those features within the image, and this can be achieved by performing convolution of the input image with certain specific filters. So we have to choose these filter values appropriately in order to extract those specific features from the image. So we will see some demonstrations of how to extract features by performing convolution of the input image with specific filters, and in the process we will also get a better understanding of how the convolution computation itself is performed, which we had seen in quite detail in the previous lecture as well, but today we will see that with some real image pixel values. So we have here an input image which is the handwritten character number 9, and we are going to convolve that input image with a filter which is going to detect the left edge of the image, wherever there is a left edge within that image. So if you notice here, what is happening is we have a window of the same size as the dimension of the filter. So the filter is 3 by 3, so we use a window of 3 by 3 which slides across the entire input image, and at each point of time as it slides through it, whatever pixels that fall within that window, they are convolved with the filter. And if you recall from the previous video, the convolution operation is performed by an element by element multiplication of the pixel with the corresponding filter value, and then adding up those values, and that gives us the output pixel value. So we have an element by element multiplication of the pixel values with the filter values, and then those products are all added together, and that summation would then give us the output pixel value for that particular specific location. So let's go through that, and as you can see here, the window is sliding across the entire image, and the slide value is 1, and we see that as the window slides, the pixels within the window are getting updated, and they are getting multiplied element by element with the filter value, and that computation, and when we add those products, that gives us the resulting output pixel value at that specific position. And that way we are now able to extract the specific feature of interest here, which is a left edge within the image. So wherever there is a left edge, because we are using a left edge filter, so this is a left edge filter. As you can see here, the filter has values of -1 in the first column, +1 in the middle column, and zeros in the rightmost column. So this filter is designed to extract the left edges within the image. So if you look at this particular area, that's the left edge in the image, and that has been extracted here, which you see by the bright red pixels in the output. So the darker the shade of the output pixels, that means there is a stronger chance of a left side edge being present in that particular region of the image. So again, we see here this particular region that should correspond to the left edge, and we get the left edge as dark pixels in the output over here. Of course, we do notice that the filter has also extracted the right edges shown by these dark blue ones, but our interest is in the left edges, which are highlighted by these red pixels, which will be basically high positive values. The corresponding right pixels will be high negative values, if you notice in the calculations, but our interest in this case is to detect or locate the left edges in the image, so which this filter is able to extract. Similarly, we can perform the convolution with a different filter, which will yield which will extract us the right edges of the input image. So the right edge in this case would be areas in this part of the image, or areas in this part of the handwritten character 9 here. So we are interested in extracting the right edges, and as you can see from here, the rightmost column is now -1, and the middle column is 1, and the leftmost column is 0. So this filter is going to extract the right edge of the input image, and as we shall see from this demonstration here, the window is sliding across the entire input image, starting from the top left corner, and it goes along up to the up to it reaches the bottom right corner, and along the way it will compute the convolution operation, which is the element by element multiplication of the pixels within the window, and then summing up those products, and that gives us the corresponding output pixel values. So as you can see here, now this particular filter has extracted the right edges of the image. So wherever there are edges on the right hand side, those have been extracted, and these are shown by the bright dark red or dark brown regions in the output here. The corresponding blue edges are the left edges, but our interest is the right edges, which we can see very clearly that this filter has extracted the right edge from the input image. So what we see is that by choosing an appropriate filter and performing the convolution operation, we can extract certain specific features. So we have seen an example of how to extract left edges. We have seen this example here, how to extract the right edge in an image or in an object within the image. And similarly, we can extract the top edge as well. So if an image or object within an image has a top edge, we can extract the top edge as well, and similarly we can do a bottom edge. So now for the top edge, we notice that the topmost row is -1, the middle row is 1, and the bottommost row of the filter is all zeros. So this filter would extract the top edge of the image under consideration. So you see this convolution operation here, wherein the window is sliding across the entire image as before, starting from the top left and until it gets to the bottom right corner of the input image. And we see clearly here that Again, here instead of the number 9, I have used here the number 4, the handwritten number 4, because we have a nice long sweep of an horizontal line, which from which the top edge of the horizontal line has been neatly extracted by this filter by performing convolution between the input image and the top edge extraction filter. And similarly, we can extract the bottom edge filter or bottom edge of the object within the image as well. So using a filter here, now instead of the top row having -1, we have the bottom row as -1s, and the top row is now all 0. So this is a bottom edge filter, and now performing convolution between the input image and this particular filter would now give us the bottom edges of the objects within this image. So as you will see here, as the window slides through the entire image, we see that we are getting the bottom edge of the input image, or the locations of the bottom edge of the input image in this output that we are getting here. So the convolution operation is quite useful in extracting features from the input image. So we clearly see that by using an appropriate filter, we are able to extract specific features from within an image or from various objects within the image, and that way convolution is a very powerful tool that can be used in computer vision applications. And of course, there are many different types of filters for extracting specific features, and we have seen here with a clear illustration how to perform the convolution operation, as well as we have seen how by using an appropriate choice of filter we are able to extract the appropriate features from an input image. Now, of course, for each type of feature extraction, there might be multiple filter options available for us. So again, we have seen the bottom edge filter previously, and this is also a bottom edge filter, but with a slight variation here. So rather than having all -1s in the bottommost row and all +1s in the middle row and all 0s in the top row, we have 1s in the top row, 0s in the middle row, and -1s in the bottom row. And this is a variation of the bottom edge filter. Similarly, we can have such variations for the top edge filters, as well as the left edge filters and right edge filters. And there are various filters that have been proposed in the literature by various researchers for various applications. So of course, by choosing appropriate filters, we would be able to extract appropriate features. So this illustration here is for the same handwritten character number 4, but with the bottom edge filter attributed to a person named Prewitt. So it's called as the Prewitt bottom edge filter. And let's see how this compares with the previous bottom edge filter that we have seen earlier. So again, the process of convolution is the same as before, where the window of the same size as the filter slides across the entire image, and at each point of time it computes the element by element multiplication of the pixels within the window with the corresponding values of the filter, and then adds those products to get the corresponding output pixel values. And we see that in this case, again, we have obtained the bottom edge locations of the input image in this particular case as well. But this is a variation of the bottom edge filter. So to see the comparison, let's put these output images of the Prewitt bottom edge filter and the previous standard bottom edge filter that we had seen earlier next to each other, and see how they compare in terms of being able to extract the bottom edge feature from the object of the handwritten character 4 within that image. So that's the comparison we have here. So that's the standard bottom edge filter which we had seen earlier, and that's the Prewitt bottom edge filter. And as you can see, the Prewitt bottom edge filter is giving us more details of the bottom edge as compared to the standard filter. So it is clearly seen that the Prewitt filter is better in terms of extracting the desired feature compared to the standard filter. So again, depending on the applications, we have different options for the filters. So we will be able to use an appropriate filter to extract appropriate features from the input image. So we can, in this particular way, extract vertical edges, horizontal edges, diagonal edges, or in fact, for that matter, we could also look for specific shapes within the image, as we are going to see next. So here we have the handwritten character number 9, and we want to extract this circular loop of the handwritten number 9 from the input image. So we want to locate where is that circular loop in the handwritten image. So the number 9 has the circular loop. So wherever there is ink, it is given by these pixel values 1, and the empty circle in the middle is given by the pixel value -1. And we want to identify where this loopy pattern occurs within the input image, and we can locate that by performing convolution operation using an appropriate filter. And this filter again here is designed to extract that loop shape. So the loop shape here is a circular shape which is having ones all around with a -1 in the middle. So what happens now is when we perform this convolution operation, we get a +1 right in the middle here, which corresponds to having this exact loop values at that location within the image. So convolution is able to locate specific patterns within the input image, and by checking at the output values of the convolution, we will be able to locate where specific shapes or patterns occur in the input image. So again, if we had written this handwritten number 9 at a slightly different location in the input image, so rather than that being right in the middle here, if it is slightly shifted to the left, the convolution operation would still be able to detect it and identify where that loopy pattern is present in the input image by giving us the value of the output pixel corresponding to that location. So we clearly see that the convolution operation enables us to get the features in the input image irrespective of where that feature is present. So we say that convolution enables position invariant feature detection of the within the input image. So it is a very powerful tool to use convolution for computer vision applications, because it can extract various features from within the input image and from within various objects within the input image. And this convolution operation lies at the heart of convolutional neural networks. So we have seen in quite length how the convolution is performed, and how the different filters are used in the convolution operation to extract specific features, and we've seen how the computation of convolution is also performed. So going forward, we will see how what are the remaining aspects of the CNN layers. Of course, apart from convolution, there are certain other functions also being performed within the convolutional neural network. So we will see what are those other operations performed by some other layers within the CNN, and how those operations are useful in achieving our end goal of being able to classifying or identifying certain objects or images, or objects within the images or the image as a whole, or to detect or identify certain objects within the image, and so on and so forth. So as a whole, the CNN architecture itself has convolutional layers as well as certain other layers which perform certain other functions, and going forward we will include those other layers and their functionalities into our discussion, and that will give us a complete understanding of how CNNs work and how the end objective of using CNNs in computer vision is achieved.